Hi everybody, and welcome to day 2 of our gas laws, where we are going to talk about 2 more types of gas laws today. And the first is what's known as Dalton's law of partial pressure. In a mixture of gases, the total pressure is the sum of the partial pressures of each gas. So if we're talking about this in terms of an equation, it would just be something super simple like this. So the total pressure is equal to the pressure of your first gas plus the pressure of your second gas plus however many more gases you may have. So a great example of this is air. All right, air is a mixture of gases, and it is mainly made up of nitrogen gas. All right, and in air, the pressure of nitrogen gas is about 79.11 kilopascals. The next major component is oxygen, which has a pressure of 21.2 kilopascals. And then there's a bunch of other stuff, all right, that we don't need to really write down, so I'll just write other stuff. That gives us a pressure of about 0.95 kilopascals. If you go on ahead and punch those into your calculator and add them up, you will get 101.3 kilopascals, which should sound very familiar because that is standard air pressure. So Dalton's law of partial pressures is simply that, is that if you have a mixture of gases, you just add up the components to get the total pressure. All right, so let's just look at 2 really quick examples. All right, so determine the total pressure of a gas, all right, a mixture that contains oxygen at 20, nitrogen at 46.7, and helium at 26.7. So I'll write it out just to be complete, but you certainly could just punch this into your calculators. All right, 46.7 kPa and 26.7 kPa. Okay, and you're just gonna add those up. And when you add those up, you should get 93.4 kilopascals. As your answer. We're just adding, okay? So let's take a look at number 2. The total pressure of a mixture of gases is 350. The first gas has a pressure of 209. What is the pressure of the second gas? Well, in this case, we are going to subtract. If the total is 350 and one of our gases is 209, all right, we are just going to subtract 209 from 350 and we get 141 kilopascals. All right, so these Dalton problems are very straightforward. So typically you don't see them as a problem all by themselves. They're going to be part of another problem. And the type of problems where you will be seeing and using, I should say, Dalton's law is when we collect a gas over water. All right, a common method of collecting gas is to collect them over water. Now, what does that mean? Well, you've got to remember we're talking about gases, all right? When you think of gases, think of things like oxygen and nitrogen. They are colorless, all right? You can't see them. You don't really know when you have them, so that can be a little bit troubling. So what we do is we will collect the gas over water, which means that we are going to use water, all right, and displace water to be able to figure out exactly how much gas we have. But when we have a gas that's been, what we say, bubbled through water, that pressure inside is both the gas we care about and it is the water. So you can kind of imagine, all right, if inside, you know, let's say imagine an upside down test tube. It's called a eudiometer. We're going to use it later, but you're going to have gas at the top. And so there's going to be gas there, but there's going to be water as well. So that water is giving off some vapor pressure, and that vapor pressure has to be calculated and dealt with in the problem. So let's take a look. For this problem, I actually want you to change this 25 to 325. So you have 325 centimeters of oxygen are collected over water at 10 degrees Celsius and 98 kilopascals. What will be the volume of the dry gas? So dry gas means without water. So dry gas means without the water. All right. So I've given you this number, this 98. So that 98 kilopascals is equal to the water vapor pressure, all right, so the pressure of the water plus the pressure of that gas. Okay, so we need to get rid of the pressure of the water. And I'm always going to tell you what the water vapor pressure is at a certain temperature. You're never going to have to guess that. So you're going to go 98 minus 1.2. All right. And that gives you 96.8 kilopascals. And that is your pressure of your gas. So we are going to use this number in our other gas law. So now let's look at the rest of the problem. You have 325 centimeters cubed of oxygen collected at 10 degrees Celsius. We now know the pressure of just the gas. What will the volume of the dry gas be at 101 kilopascals and 20 degrees Celsius? So now this turns into a combined gas law problem. And if you recall from our last notes, V1, P1, T2 is equal to V2, P2, T1. I'm looking for V2. All right. So I'm going to divide each side by P2, T1. So remember, I like to do my algebra first. All right, because I just think it works out nice and makes it nice and organized. So my original volume is 325 centimeters cubed. So 325 centimeters cubed. My original pressure we figured out is the pressure of this gas. So that's 96.8 kPa. My final temperature, all right, so remember, be careful, that's final temperature in the numerator. All right, so my final temperature is 20 degrees Celsius, so that's 293 Kelvin, because 20 plus 273. My final pressure is 101. And my initial temperature is 10, so that's going to be 283 Kelvin. I'm going to punch all those numbers into my calculator. You might want to pause and do that for yourself now. And you should get an answer of about 322, we'll say 0.5 centimeters cubed. I'm not so worried about significant figures here, so just going ahead with that answer. All right, great. So we're going to move on and do a little bit more challenging Dalton's problem. All right, so let's take a look at this one. And I know there's a lot going on in this problem, but I will walk you through it. 3 flasks of gas are hooked together to allow for the gases in each one to freely flow into each other. If flask A is 3.2 liters and under a pressure of 650, flask B is 5.1 liters and under a pressure of 935, and flask C is 2.8 liters and under a pressure of 112. What will be the total pressure when the valves are open and the gases can move between the flasks? So the first thing I want you to do is to kind of sketch this out. And that's what we're going to do together to give us an idea as to what am I talking about. So I'm dealing with flasks and I'm not a very good artist, but you'll get the idea. So here's my first flask. And I told you that it is 3.2 liters. This is flask A. And it has a pressure of 650 millimeters of mercury. All right, great. Flask B is, and I'll just make it a little bit bigger flask, okay? Because B here has a volume of 5.1 liters, okay? And its pressure is 935 millimeters of mercury. All right, so then in flask C, we have a flask that is the smallest of our 3, and it's 2.8 liters, all right? And it has a pressure of 112 kPa. All right, so we have these 3 flasks, but we have a way to connect all 3. They're not connected yet, but when we do connect them, all right, the volumes are going to be the addition of all of these 3. So what we need to do to solve this problem, all right, is actually, is actually several of our gas laws. So let me have your calculators out, please. All right, great. So before we get started, let's kind of notice something that's going to be a problem for us later. All right, and that is that this one is in kilopascals. I'm going to go ahead and convert that one to millimeters of mercury so all of my pressures match. So I'll just do that over here, 112 kPa. All right, 760 millimeters of mercury, 101.3 kilopascals in the denominator. So I'm going to go 112 times 760 divided by 101.3. And that gives us about 840. So instead of that number, I'm going to use 840 millimeters of mercury. Okay, great. So what we need to do for this, all right, is first figure out what's going to happen to each individual gas. So let's first talk about gas A. Gas A is starting at 3.2 liters and it has 650 millimeters of mercury. When I connect all of these, it's going to have a new volume, and that new volume is the addition of all three flasks, because when I connect them, you can just assume that my little connections don't have any volume themselves. When I connect them, these gases are going to flow freely throughout these three containers. So we're going to go 3.2 plus 5.1 plus 2.8, and this gives us our new volume. All right, so my new volume is going to be, so V2 is going to be 11.1 liters, because when I add it up, 3.2 plus 5.1 plus 2.8, I get 11.1 liters. Well, I want to figure out for flask A, my gas went from 3.2 liters to 11.1. What's going to happen to my pressure? If you notice here, I don't talk about temperature at all, so temperature remains constant. So this is actually going to be a Boyle's. We're going to do several Boyle's law problems. Okay, and Boyle's law, remember it's V1 P1 is equal to V2 P2. So I'm looking for P2, and P2 is going to be V1 P1 over V2. So let's go on ahead and do that for A. So my initial volume was 3.2 liters. My initial pressure, 650 millimeters of mercury. My final volume is now the volume of all three flasks, which is 11.1 liters. I'm going to punch that in and I get about, let me just double check my math here. So I get 3.2 times 650, enter, divided by 11.1. And yeah, I get about 187.4 mmHgs, because your liters divided out. All right, so now I'm going to do the same thing for B. Okay, so for B, my initial volume, again, we're using the same Boyle's law. My initial volume was 5.1 liters. My initial pressure is 935 millimeters of mercury. And my final volume for B is also 11.1 liters. Okay, when I punch that in, I get 429.6 millimeters of mercury. I'm now going to do the same for C. This is getting repetitive, I know. All right, but for C, our initial volume is 2.8 liters. Our initial pressure, remember we figured out, is 840 millimeters of mercury. And again, our final volume is going to be the same because we've now connected these three flasks. And this gives me 211.9. Okay. Now and this is millimeters of mercury. So far I actually have not used Dalton's law. I'm about to. You now have a system of all three of these volumes that has a volume of 11.1. The total pressure inside that 11.1 liters is going to be the addition of these three gases. So we're going to add, this is A, this is B, this is C. We're going to add those three up, get about 828.9 millimeters of mercury is the total pressure of the system. Okay, so this is a little bit of a challenge problem, but that's okay. This gives you an idea as to the types of things and ways that we can see Dalton's law. All right, so we are going to do one more gas law today, and that gas law is going to be dealing with what is known as diffusion. And when we talk about diffusion, we're talking about the random scattering of gas particles. All right, just like in biology, diffusion of a substance, of a gas, is going to go from areas of greatest concentration to areas of lower concentrations. Okay? All gases do not diffuse at the same rate. Okay, here we go. At the same temperature, molecules of a smaller mass will diffuse faster than molecules of a larger mass. And that makes sense, all right? The smaller you are, the faster you have to go to maintain temperature. So let's just kind of look at the equations for this, and I'll show you what we're going to be using. So we know, all right, kinetic energy is the energy of motion, all right, and we're saying that we are at the same temperature. So if we're at the same temperature, the kinetic energy of your first gas must equal the kinetic energy of your second gas, because temperature is a measure of the average kinetic energy. All right, we know that kinetic energy is dealing with mass and velocity. So if we play around with the kinetic energy equations, and you don't have to do this algebraically, I'm telling you right now, we would get the velocity of your first gas over the velocity of your second gas is equal, this is going to be the equation we're going to use, of the mass of your second over the mass of your first. All right, so this is going to be the equation that we use for what is known as Graham's law. Okay, so this is the Graham's law equation. Now, we will not be solving for individual velocities. Instead, we solve for this V1 over V2 as a single entity, and we call this, and I'm going to write this right under here, the relative rate of diffusion. All right, so let's see what this is going to look like. Okay, so Graham's law states that the relative rates at which two gases under identical conditions of temperature and pressure will diffuse varies inversely as the square roots of the molecular mass of the gas. All right, so again, let's just going to rewrite this equation here for us. So V1 over V2 is going to be equal to the square root of M2 over M1. All right, so let's see how this is going to work out for us. So there's two types of problems. The first is just if I ask you for the relative rate of diffusion. Compute the relative rate of diffusion of helium and argon. Very straightforward. You're going to go, helium is your first one listed, so go make that one, make argon your second. Okay, so again, V1 over V2 is equal to the square root of M2 over M1. So we're going to be solving, excuse me, for V1 over V2. All right, great. Well, what do I mean by M's? The M's are going to be the molecular masses. So we're going to find those, all right, on your periodic table. So find those on your periodic table. So what I'm going to have here is, so the square root of the mass of 2, which is argon, right? Argon over the mass of helium. All right, and if we look on the periodic table, argon has a mass of 39.9. Helium has a mass of 4. All right, we're going to divide those, take the square root, and you should get 3.2. So how do we answer this question? We've done some math, but we haven't answered anything. So what this tells us is that helium diffuses 3.2 times as fast as argon. That would be my final answer. And it makes sense. Helium is much lighter than argon. All right, so helium should be diffusing faster. Okay, so the second type of problem that I can give you is I can give you the relative rate of diffusion and ask you for the molar mass or molecular mass of the unknown gas. So methane diffuses 1.66 times as fast as an unknown gas. What is the molecular mass of the unknown gas? So methane is going to be my gas 1. I mentioned it first. Your unknown is going to be gas 2. So we know our relative rate of diffusion, we can go back to our equation here, is V1 over V2. We already know that that's 1.66. And that's going to be equal to the square root. All right, methane, we should know what methane is. Remember from our organic unit, methane is CH4. All right, so methane, CH4. Molar mass of methane is 16. So that goes in the denominator. All right, because our M1 goes in the denominator. Remember the equation. And then we don't know the unknown gas, so that's going to get our X. Okay, so this is what we're going to use to solve. So we want to get rid of this square root, so we're going to square each side. Okay, and when we do that, okay, so 1.66 times 1.66. All right, so that's going to give us about, I'll write it over here, 2.76 is going to be equal to x over 16. Okay. And when you multiply 16 by 2.76, you get about 44.1. The label for this, and I would be kind of understanding either way, is grams per mole technically because it is the molar mass. All right, but that is how you do that problem. Okay. All right. So far we have learned about Boyle's law, Charles's law, Gay-Lussac's law. We put those three together into the combined gas law. And then today we learned about Dalton's law and about Graham's law. All right. I hope you've enjoyed it. We'll do plenty of practice. Have a great day.